Hello and welcome to Enhanced Biological Phosphorus Removal. In this presentation, I want to cover the procedure of how we can grow bacteria in wastewater treatment that are going to store more phosphorus than the normal bacteria would, and we'll talk about some of the um, different good and bad things associated with that, and different tools that we can look at to use in terms of monitoring these processes. So why is phosphorus removal important in wastewater? I'm going to stop my video so you don't have to watch me the whole time. Phosphorus removal is important because if we have too much phosphorus that's entering the receiving water bodies, that phosphorus is going to promote growth of algae and undesirable aquatic life that will eventually change the whole characteristics of that water. So, for example, if you have too much phosphorus, you can lead to algae blooms, which then create diurnal oxygen variation in the receiving water bodies, and can be bad for fish. And there's a downhill effect on the whole food chain, in addition to the recreational usage, and eventually that water is going to be used for recreation and potentially being cleaned for drinking water. So everything is all interconnected, and since they've passed some of the laws in the 1970s, we have seen in the United States here a very good improvement of our water bodies, our lakes and rivers and things like that. So it's very important for the environment that we keep the phosphorus low in the receiving bodies, and in wastewater, we're actually in many cases putting out lower amounts of phosphorus that would be in those bodies originally with runoff and other things. So we'll get into the dynamics of that a little bit more as we go. So how does phosphorus end up in wastewater? We have domestic wastewater, so anything that we use when we're flushing the toilet, that type of material. Also the gray water from showers and sinks, everything like that's going to come, and that can have phosphorus. There's industrial water softening. There's very commonly polyphosphate is added to drinking water to prevent corrosion in pipes. So that's another source of phosphorus that eventually ends up in the wastewater. There's a lot of phosphorus in detergents and other boiler waters, as well as different industrial wastewater treatment processes can have varying degrees of concentrations of phosphorus. So pure phosphorus is very rare in nature, and most of the time phosphorus is going to be combined with oxygen molecules. So very often we're going to look at phosphorus in terms of orthophosphate. So we have organic phosphorus, which is carbon-based, found in plant and animal tissue. And then there's also inorganic phosphorus that's not associated with organic material. One thing that's very important is when we do testing, we want to make sure that we're reporting phosphorus and we're understanding it's reported in the correct way. So for example, if your effluent limit is in total phosphorus, you want to make sure that you're reporting that as total phosphorus. So you can report reactive phosphorus as PO4-3, which would be reactive phosphate or orthophosphate, and that's going to be considerably higher than your actual phosphorus is P. So you can convert that phosphate to phosphorus is P by multiplying the phosphate by 0.3261 as a conversion factor. So if you have a spectrophotometer or any testing equipment like that, it's very important to make sure that you know what form of phosphate you're testing for, and you also are reporting it in the form that calls for. So very often the testing equipment is going to report as orthophosphate, and you may need to convert that because most limits are going to be phosphorus reported as P. So there's some other tests for phosphorus. When we look at orthophosphate, that's going to be generally, what's readily available, and there's not a whole lot of steps in the testing, so it can be measured very quickly. Then there's some acid hydrolyzable phosphate, which you can always filter or not filter sample. That's going to separate your dissolved from your particulate, and you're going to convert with this acid digestin other forms of polyphosphate or phosphate to ultimately orthophosphate. So through this digestion process in the lab, you're basically converting other forms of phosphorus into orthophosphate, which then you're going to report as either orthophosphate or phosphorus as P. So there's different tests. Total phosphorus is going to measure everything. Again, you can filter it where you'd have your dissolved total phosphorus versus you can have total phosphorus as total phosphorus. But the main thing is to understand that there's a lot of different forms of phosphorus, and the dissolved reactive phosphorus or the orthophosphate is really going to be the most essential in terms of that's the phosphorus that's readily available for bacteria and wastewater treatment plants. One quick side note is the dissolved non-reactive portion can vary. So there is some phosphorus that is just not able to react with anything, and that can be proven out through testing. And in some instances, you can get a variance for a wastewater permit if you can prove that you have dissolved non-reactive phosphorus, because there's basically you're not going to be able to remove it, and it's also not going to be detrimental to any receiving water bodies. So when we look at normal phosphorus in domestic or municipal wastewater treatment processes, generally about 6 to 9 milligrams per liter of total phosphorus, in addition to about 200 milligrams per liter of BOD is what you would tend to see. So if you have industrial wastewater sources or septics, things like that, that can definitely change those ratios. And then every plant's going to have, certain limits they need to meet. Some plants are limited for the amount of phosphorus they can discharge, and others aren't. And eventually, we're on a trend where eventually most plants are going to end up with some form of a phosphorus limit. So those limits can be based on a lot of different things: concentration, amount of pounds discharged. Ultimately, it's usually dependent on what the receiving water body from the wastewater treatment plant, the aquatic life and what that needs to be. So depending on where you discharge, that's often a very big indicator of how tight those limits may be. So we are going to get some phosphorus removal that just occurs through BOD removal and BOD degradation. So most bacteria that we have in wastewater generally contain 2 to 3% phosphorus by dry weight. So for every 100 parts or milligrams per liter BOD removed, about 1 part phosphorus is removed and basically incorporated into the cells of the new bacteria. So in most municipal wastewater processes, if we're going to get some degree of phosphorus removal where that phosphorus is just getting eaten up by the bugs, and then eventually it's wasted and it's removed through wasting. But that's going to generally leave behind anywhere between about 3 to 5 milligrams per liter left over. And if you have a limit of, for example, 1, then that's going to leave more that you would have to remove beyond what would naturally happen. So that can be accomplished through chemical phosphorus removal. And regardless of, plants that have and use enhanced biological phosphorus removal, where the bugs are doing the majority of the phosphorus removal, it's also important to have some backup equipment, because those processes, there's a lot of things that we'll get into through this presentation that can negatively impact them. So the chemical phosphorus removal is necessary, and it's something to have as a backup. And in some cases, as we'll discuss, there are some individual circumstances where, when you look at a case-by-case situation, there are times where chemical phosphorus removal may make more sense than enhanced biological phosphorus removal. So it's always everything in wastewater. There's always a lot of factors that go into these certain decisions. So we can remove phosphorus through chemicals such as alum, lime, ferric and ferrous chloride, or ferrous sulfate, and some other chemicals that it could be used. So when we rely on chemical phosphorus removal, there are some disadvantages: the price of the chemical, the operational cost. You're going to create additional sludge, and you're also going to decrease alkalinity with a lot of those different different chemicals, and that could, depending on where you're located and how much nitrification, things like that are occurring, there could be some significant disadvantages with that. Some advantages with chemical phosphorus removal is it's very reliable, and it's easy to retrofit and basically add chemical phosphorus removal if you need to. And there's a lot of emerging technology where you can also monitor the orthophosphate online and basically dose chemical accordingly. So you only use what you need to in terms of your chemical and the associated costs with that. So enhanced biological phosphorus removal, the goal is really to encourage a population of bugs in your wastewater treatment plant that are called PAOs. And PAOs, polyphosphate accumulating organisms, are going to store and have a higher phosphorus concentration by dry weight than most of your other bugs in wastewater would. So generally, you're going to have about 2 to 3% of your normal wastewater bacteria. They're about 2 to 3% phosphorus by weight. And if you have a stable PAO population, that percentage could be up to around 6%. So you're basically growing bugs that are just going to naturally take up more phosphorus than the bugs that would otherwise compete in wastewater. So some of the advantages and disadvantages of enhanced biological phosphorus removal. The advantages is you're going to reduce the need for chemicals, alkalinity loss, the extra sludge, the cost associated with everything like that. There's also some instances where it can improve the settling. And we'll talk about later, there's some instances where that can also be problematic as well. So disadvantages of enhanced biological phosphorus removal is there's some capital cost, baffles, mixers, and it's going to be more complexity as far as getting the conditions right to have a present population of PAOs in the system. So just some general terminology. Aerobic would be a condition in which free and dissolved oxygen are available. Anoxic is a condition where you're going to have combined oxygen, so nitrate, sulfate. Then anaerobic would be there's no free or combined oxygen available. And in the selector zone, the anaerobic zone, we need to have the ORP, which we'll talk about. We have to have that low enough in an anaerobic setting for that process to work. So we will get back to some of this terminology as we talk about it a little bit more, just so this flows a little bit better and makes a little bit more sense. General criteria for enhanced biological phosphorus removal. when you look at the influent BOD to total phosphorus ratio, generally, if it's greater than 25-1, it's a good candidate for BioP. COD 45-1 would be kind of a recommendation. So actual numbers are very plant specific, and it's also very dependent on what is the BOD like, because not all BOD is the same. And we're going to talk about the differences in your BOD versus, so basically you have particulate BOD, you have soluble BOD, and then you have organic acids, which are a form of soluble BOD that can be taken up really quickly and really accessible for the bacteria. So to understand that process, we have this diagram here of absorption versus adsorption. So when you have BOD that's very readily available, you can think of the that red circle there as kind of the cell membrane, with the outer being kind of the mouth of the bacteria. And soluble food's going to go directly into the in the cell, where it's either going to be oxidized or stored. Then you have other material that would be adsorbed, where the bugs are going to kind of catch it on the outside, and then eventually enzymes and other things are going to break that down. So a good analogy would be, that would be more of like your higher glycemic, or like oatmeal, those types of, where it takes a little bit longer to become available. So for enhanced biological phosphorus removal to be successful, we need to have BOD or food in the form of volatile fatty acids, or you're going to hear me say organic acids, volatile fatty acids, fairly interchangeably. So septicity occurs when the bacteria ferment BOD to smaller pieces, which are the organic acids. So these smaller pieces are formed because basically, if there's no oxygen electron receptor to create new biomass, what you're getting is you're just getting this fermentation where you're getting the beginnings of anaerobic treatment, but not the full anaerobic. So you're just getting this conversion of longer chain to shorter and more readily available, such as acetic acid and propionic acid. So sources of organic acids, the lift stations, everything in the collection system, basically any area where you're going to have BOD and you're going to have bacteria, which are naturally present in BOD and conditions where you don't have oxygen. So if you have that ingredients for fermentation, you're going to get the creation of organic acids. You're also going to probably have a lot of different industrial wastewater plants. Septage is going to have a lot of septicity and organic acids. And then there's also areas of the treatment plant where organic acids can be formed. And we'll talk about how that can become kind of a double-edged sword, where it can be really beneficial for biological phosphorus removal in the right amounts. But if we have too much septicity, it can also cause some trouble. So basically, in enhanced biological phosphorus removal, we have a two-step process in which we have an anaerobic environment, an anaerobic selector, and it's followed by your aeration basin. In the anaerobic selector, the PAOs, the bugs that we want, release orthophosphate to obtain the energy to uptake readily biodegradable organic material. So the VFAs, that soluble, readily available food, when they're in the anaerobic zone, they're going to take up the VFA and they're going to re-release orthophosphate. And then in the aerobic zone, the PAOs are going to grow new biomass. They're going to oxidize the food that they had stored as PHA, is what they convert the BOD to. And then they're going to replenish the amount of phosphorus that they used. So by the PAOs having a higher amount of dry weight phosphorus than other bugs, once you have a population of those, you're going to get more phosphorus removal from having those. So looking at the influent, let's say you have 5 milligrams per liter of total phosphorus. You may see an orthophosphate. You're going to generally get a release of maybe 2 to 3 times what your influent is. So you're going to see in a successful biological phosphorus removal process where you're going to see that phosphorus increase from the influent in the anaerobic tank. So you may see 5 in the influent and 15 to 20 in the anaerobic. And then as you get to the aerobic and you start to get those POs, it's a process called luxury uptake where they're really rapidly recovering that phosphorus that they had to release in order to store that food in the anaerobic zone. You can get very low phosphorus left over residually. So monitoring the ORP value in the selector zones is probably our best tool in terms of getting the right conditions, because if we have too much food in the selector, we can have food passing through, and that can cause trouble and bacteria growth that we don't want. And the same thing is if we have an underloaded selector, we're going to lose our BioP, and we can also create conditions that are, you can have some VFAs that just kind of pass through because you're underloaded as well. So generally ballpark values about minus 300 millivolts for anaerobic and minus 100 millivolts for anoxic. But that's gonna differentiate depending on what you see successful, and it's oftentimes fairly plant specific. So if we want to decrease the ORP value in the selector, so if the ORP value is too high, we want to create a higher F to M, so a more amount of food in proportion to the microorganisms available. So how do we do that? We can decrease the RAS rate. That's going to send less bugs back into the selector zone, also less nitrate. If there's an internal recycle flow, MLSS, could decrease that. That's going to make the strength of the waste in the selector higher to make it more septic and a lower ORP value. And then you can also supplement carbon. So basically giving it more food to drive that F to M higher, to drive the ORP lower. Or you can try to make more VFAs, sometimes holding the solids in the primary a little bit longer, or there are some instances where plants may have like a fermenter. So this slide here would basically showing a process where you're recycling that primary sludge into this mixing tank to mix the primary with the influent and really ripen everything up. So there's a lot of different versions of fermenters, and basically plants that have a fermenter, the longer you keep that sludge in the fermenter, the more you're going to promote septicity and the formation of volatile fatty acids. This slide here is kind of covering what we talked about with the underloaded and overloaded selectors. So it's very important that the ORP value is in a good zone. And if it's chronically outside of the target values, underloaded or overloaded can both be equally bad in terms of biological phosphorus removal and also in terms of the microbiology that you grow in your system. So the ORP values and the operational tools are all really important for getting it right. There is some phosphorus from side streams that we have to take into consideration. So sludge dewatering and centrate from anaerobic processes are generally going to be really high phosphorus, and that can change that BOD to P ratio. And if we have too much phosphorus carry over, even if we have BioP, we can end up with more left over in the effluent. So there's different ways to look at that, and it's oftentimes very plant specific. And in terms of sludge retention time or sludge age and BioP, there's a lot of room. So the PAOs tend to operate really well on a broad range of SRT. And one of the things that we'll show is there's a very high genetic diversity within PAOs, and I suspect that that's one of the main reasons why you can have some plants that tend to have better PO or BioP at 30-day SRT versus others that may be 3 to 4 days, and that's kind of their sweet spot. So if excessive SRT values, if the sludge is too old, that can create a secondary release of phosphorus. So when the bugs die, they're going to re-release orthophosphate through cell lysis. And so if the sludge becomes too old, you might be doing good on the front end, but then on the back end of the system, they're dying and it's re-releasing phosphorus. Additionally, if the sludge sits in the final clarifier for too long and that ORP value becomes low enough, you can also get a re-release of orthophosphate. So those are all different things to check. A lot of times the PAO and biological phosphorus removals can be really finicky. This slide here is just demonstrating the different genus that are capable of enhanced biological phosphorus removal. And you can see some of them, they're all PAOs, but some are also, capable of denitrification, and like a Cumulobacter can also be a GAO if the conditions are right. So very often the bugs that you need are there, but if the conditions aren't right, they can switch and they can become GAO instead of PAO, or they can denitrify and other things. So there's a lot of complexities that we're learning as we're learning more about these processes. One thing of note is fats, oils, and grease. When they are exposed to septicity, they become more readily available for filaments like microthrics or Nocardia, which I refer to as Actinomyces miculata. So it's common in some situations where if a plant does implement a selector zone and it goes to biological phosphorus removal, even if the FOG, fats, oils, and grease stays the same, now that you've introduced the septicity, that can promote certain filaments. And there are some filaments that do compete very well in the selector. So your anaerobic selector in general is going to select for good bacteria, but there are some uninvited guests that it does have the potential to help select for. So, you can look at the root cause, and in both of these cases, the fats, oils, and grease is the root cause. And, if they're there and they're septic, then it becomes more likely for problems with microthrics or Actinomyces miculata filaments, things of those nature to develop. So it's always a case by case thing, but there are some instances where, perhaps at certain times of the year, if it's a small plant and the microthrix likes the cold weather, there's times where from an operational standpoint, maybe, chemical phosphorus removal in the winter versus, trying to get BioP and then, seeing higher microthrix. But, there's always, there's no right or wrong thing. There's a lot of different things, and you have to make sure that you're, optimizing and doing what's best for your individual circumstance. One consideration, if you have biological phosphorus removal occurring, is you're going to have a significantly higher amount of phosphorus per dry weight of the bacteria. So if you have a limit and you have more PAOs in the system, you're going to get much closer to that phosphorus limit with, significantly less suspended solids in the effluent. So for example, you can see at 15 parts per million, you're already at 15 milligrams per liter TSS in the effluent, you're already getting close to 1 milligram per liter total phosphorus. And that's just, that total. So basically as you have BioP, you're going to be storing more phosphorus in the sludge, and any solids that leave the plant are going to have an impact on the total phosphorus limits. Other thing to be aware of would be the land application considerations. Usually it's dependent on the amount of phosphorus that can be applied per area. So obviously if you have higher phosphorus in your sludge, that may impact those considerations. So those are all different things that need to be kind of put into perspective and in terms of what you end up doing. So I hope you found this video interesting and entertaining and practical, and the references are cited here. And I can also be reached at Ryan@rhwastewatermicrobiology.com. All right, thank you.